the universe's deepest secrets, 9 cosmic mysteries science can't explain yet. Episode 1, The Dark Universe. Introduction. The universe as we know it, stars, planets, galaxies, and all forms of observable matter, makes up a mere 5% of the cosmos. The remaining 95% is invisible to our telescopes and detectors, yet exerts profound gravitational influences that shape the very structure of our universe. Welcome to the Dark Universe, a realm dominated by mysterious components known as dark matter and dark energy. These invisible forces constitute the greatest unsolved mystery in modern astrophysics, challenging our fundamental understanding of physics and the cosmos itself. The mystery of dark matter. The discovery of missing mass. In the 1930s, Swiss astronomer Fritz Zwicky made a startling observation while studying the Coma cluster of galaxies. The galaxies within the cluster moved so rapidly that they should have escaped the cluster's gravitational pull, yet they remained bound together. Zwicky proposed that some form of missing mass, or dunkle materia, dark matter, must be present, providing the additional gravitational force needed to hold the cluster intact. This observation was largely overlooked until the 1970s, when American astronomer Vera Rubin conducted detailed studies of galaxy rotation. Rubin discovered that stars at the edges of spiral galaxies orbit at nearly the same speed as those closer to the galactic center, contradicting the laws of physics as we understand them. According to Kepler's laws, stars at greater distances should orbit more slowly, just as the outer planets in our solar system move more slowly than the inner planets. The only explanation for this flat rotation curve was the presence of a massive, invisible halo of matter extending far beyond the visible boundaries of galaxies. This material couldn't be seen through telescopes, didn't emit or absorb light, and interacted with normal matter primarily through gravity. Dark matter had moved from fringe theory to scientific necessity. Properties and composition. What exactly is dark matter? Scientists have determined several key properties. It doesn't interact with electromagnetic forces, light. It doesn't emit, absorb, or reflect radiation. It interacts primarily through gravity. It's distributed in halos around galaxies and permeates galaxy clusters. It comprises approximately 27% of the universe's total mass energy. Leading theories suggest dark matter consists of yet undiscovered subatomic particles. The most compelling candidates include WIMPs, weakly interacting massive particles, theoretical particles that interact via weak nuclear force and gravity, with masses 1 to 1,000 times that of protons, axions, extremely light hypothetical particles originally proposed to solve problems in quantum chromodynamics. They could be abundantly produced in the early universe. Sterile neutrinos, theoretical cousins of standard neutrinos that interact only via gravity, potentially explaining dark matter's elusive nature. Alternative theories propose modifications to our understanding of gravity itself, such as modified Newtonian dynamics, M-OND, which suggests gravity behaves differently at galactic scales. However, these theories struggle to explain the full range of dark matter observations across cosmic scales. Detection efforts. The hunt for dark matter involves multiple experimental approaches. Direct detection, deep underground laboratories like Gran Sasso in Italy, Xenon at the South Dakota, Sanford Underground Research Facility, and PandaX in China use sensitive detectors attempting to capture the rare interactions between dark matter particles and normal matter. These experiments typically employ large tanks of ultra-pure materials like liquid xenon, shielded from cosmic rays and background radiation. Indirect detection. Observatories like the Fermi Gamma Ray, Space Telescope, and the IceCube Neutrino Observatory search for products of dark matter, particle annihilation, or decay, which might produce detectable gamma rays, neutrinos, or other particles. Particle accelerators. The Large Hadron Collider at CERN attempts to create dark matter particles through high-energy collisions, which would be detected as missing energy in the collision aftermath. Despite decades of increasingly sophisticated searches, dark matter particles have yet to be conclusively detected, deepening the mystery surrounding their nature. The enigma of dark energy. The accelerating universe. In 1998, two independent teams of astronomers set out to measure how cosmic expansion was slowing down due to gravity's pull. Using type Ia supernovae as standard candles to measure vast cosmic distances, both teams made an astonishing discovery. The universe wasn't slowing down at all. It was accelerating, expanding at an ever-increasing rate. This acceleration requires an enormous amount of energy working against gravity, uniformly distributed throughout space. Scientists name this mysterious force dark energy, and subsequent measurements indicate it constitutes approximately 68% of the universe's total mass energy budget. Theories and models. Several theoretical models attempt to explain dark energy. Cosmological constant. First proposed by Einstein and later rejected by him as his greatest blunder. This model suggests space itself possesses inherent energy, creating a repulsive gravitational effect as space expands. This aligns with quantum field theory predictions of vacuum energy, though calculated values differ from observations by up to 120 orders of magnitude, perhaps the most severe discrepancy in all of physics. Quintessence. This theory proposes a dynamic energy field that varies across time and space, potentially explaining why cosmic acceleration began relatively recently in the universe's history. Modified gravity. Some theories suggest that Einstein's general relativity needs modification at the largest scales, possibly eliminating the need for dark energy altogether. Each model makes specific predictions about how the universe's expansion rate has changed over time, guiding observational tests that might distinguish between competing theories. Cosmic structure and formation. Dark matter's role in galaxy formation. Detailed computer simulations reveal dark matter's crucial role in cosmic evolution. In the early universe, dark matter clumped together under its own gravity, forming a vast cosmic web of filaments and nodes. This scaffolding attracted normal matter, which eventually condensed to form galaxies and galaxy clusters. Without dark matter, the formation of structures we observe would be impossible. Normal matter alone couldn't clump efficiently enough in the early universe to create the rich tapestry of galaxies we see today. The largest structures in the universe, superclusters spanning hundreds of millions of light years, trace out the underlying dark matter distribution, revealing its influence on cosmic architecture. Mapping the invisible universe. Modern surveys employ ingenious techniques to map dark matter's distribution. Gravitational lensing. Dark matter's gravity bends light from distant galaxies, creating distortions that astronomers measure to reconstruct dark matter distribution. Projects like the Dark Energy Survey, an upcoming Euclid mission, use this technique to create detailed maps of dark matter across vast cosmic volumes. Galaxy clustering. The spatial distribution of galaxies serves as a tracer for the underlying dark matter structure. Massive spectroscopic surveys like DESI, Dark Energy Spectroscopic Instrument, measure precise positions for millions of galaxies to reveal the cosmic web. These maps confirm predictions from the Lambda CDM model, Lambda Cold Dark Matter. Matter, currently our standard cosmological model, incorporating both dark energy, lambda, and cold dark matter, while highlighting remaining puzzles in small-scale structure. Frontiers and future directions. The Dark Energy Survey and beyond. Major astronomical initiatives are dedicated to unraveling dark universe mysteries. The Dark Energy Survey has mapped over 300 million galaxies across 5,000 square degrees of sky, providing unprecedented constraints on dark energy properties. The Dark Energy Spectroscopic Instrument, DESI, will measure redshifts for over 30 million galaxies, creating the most detailed 3D map of our universe to date. Looking further ahead, NASA's Nancy Grace Roman Space Telescope and the European Space Agency's Euclid mission will provide revolutionary insights into dark energy by observing billions of galaxies with unprecedented precision. Theoretical challenges. The dark universe presents profound theoretical challenges. The cosmological constant problem, why vacuum energy is so much smaller than quantum theory predicts, remains one of physics' greatest unsolved puzzles. The coincidence problem questions why dark energy became dominant at roughly the same cosmic epoch when intelligent observers evolved, raising troubling questions about anthropic reasoning in cosmology. Some theorists propose connections between dark matter and dark energy, suggesting they might be different manifestations of a single underlying phenomenon. Others explore more exotic possibilities, including modified gravity theories, extra dimensions, or the influence of adjacent universes in a larger multiverse structure. Conclusion: the dark universe represents both the frontier of observational cosmology and a profound challenge to theoretical physics. Dark matter and dark energy, comprising 95% of our cosmos, remain fundamentally mysterious despite decades of intensive study. Their existence points to missing pieces in our understanding of fundamental physics, gaps that likely require revolutionary new concepts beyond the standard model of particle physics and perhaps even beyond Einstein's theory of general relativity. As new telescopes, detectors, and experiments come online in the coming decades, we stand at the threshold of potentially revolutionary discoveries. The solutions to these dark mysteries will not only explain the cosmos we observe, but may fundamentally transform our understanding of space, time, matter, and energy themselves. The dark universe isn't simply an astronomical curiosity. It represents the clearest signpost pointing toward the next great revolution in physics, one that may ultimately reveal the deepest nature of reality itself. Episode 2: Cosmic Voids and Supervoids. Introduction. In the vast tapestry of the cosmos, galaxies are not distributed uniformly. Instead, they form an intricate web-like structure, often described as the cosmic web. Within this grand architecture, astronomers have discovered enormous regions of near emptiness, cosmic voids and supervoids, that stretch across hundreds of millions of light-years. These colossal empty bubbles represent some of the most extreme environments in our universe, yet remain poorly understood. Far from being mere absences, these cosmic voids might hold crucial clues about the fundamental nature of the universe, dark energy, and potentially even evidence of physics beyond our current models. The cosmic web, structure of the universe, the largest pattern in nature. When viewed at the grandest scales, our universe resembles an elaborate sponge-like network. This cosmic web consists of filaments, dense, thread-like structures where galaxies are concentrated; nodes, dense clusters where multiple filaments intersect; sheets, flattened planes of galaxy concentrations; voids, nearly empty regions between filaments and sheets. This structure emerged from tiny quantum fluctuations in the early universe, amplified by cosmic inflation and gradually enhanced by gravity over billions of years. The delicate balance between the universe's expansion and gravity's pull has sculpted this remarkable pattern, the largest coherent structure in nature. Discovering the voids. The first hints of the universe's bubbly structure came in the late 1970s when astronomers Stephen Gregory, Laird Thompson, and William Tift noticed a curious pattern in galaxy distributions. Their suspicions were confirmed in 1981 when astronomer Robert Kirshner and his colleagues discovered what became known as the Boötes void, pronounced Bo-O-Ts, an enormous spherical region approximately 330 million light-years in diameter containing almost no galaxies. This discovery was revolutionary, challenging the prevailing assumption that galaxies would be distributed relatively uniformly throughout space with only minor clustering. Subsequent sky surveys revealed that such voids weren't anomalies, but fundamental features of cosmic structure. Modern observations have confirmed that approximately 60% of the universe's volume consists of these vast, underdense regions. The Great Emptiness, major void systems. The Boötes void, the Great Nothing. The Boötes void remains one of the most famous and perplexing cosmic structures. Located approximately 700 million light-years from Earth in the direction of the constellation Boötes, this colossal bubble spans nearly 330 million light-years, a volume that could contain about 10,000 galaxies based on average cosmic density, yet fewer than 60 have been observed. Often called the Great Nothing, the Boötes void is so large that if our Milky Way were positioned at its center, we wouldn't have discovered other galaxies until the 1960s. Astronomer Greg Aldering once described it as what you'd expect if you went outside the universe, highlighting its profound emptiness. Various theories have attempted to explain the Boötes void's extreme underdensity. It might represent multiple smaller voids that have merged. It could result from unusually powerful ancient supernova explosions that swept matter outward. Some speculate it could be evidence of cosmic structures existing before the Big Bang. Fringe theories even suggest advanced civilizations might have migrated away from this region. Local void and other notable emptiness. Closer to home, the local void exerts significant influence on our cosmic neighborhood. Located adjacent to the local group, the galaxy cluster containing our Milky Way, this void spans approximately 150 million light-years and notably affects local galaxy motions. Our local group is actually moving away from the local void at approximately 631 kilometers per second, a void-pushing phenomenon that contributes significantly to our galaxy's motion through space. Other remarkable void structures include the Giant Void, a massive underdensity spanning about 1.3 billion light-years, discovered in 2007 in the constellation Eridanus. The Sculptor Void, a large emptiness relatively near the Milky Way that influences local galaxy distribution. The Northern Local Supervoid, an enormous underdensity that may be connected to the mysterious cold spot in the cosmic microwave background. The Cold Spot, Anomaly, a window to the multiverse, unexpected temperature fluctuation. In 2004, analysis of data from the WMAP, Wilkinson Microwave Anisotropy Probe, satellite revealed an unusually cold region in the cosmic microwave background, CMB, the relic radiation from the early universe. This cold spot, approximately 0.00015 degrees Celsius colder than its surroundings, spans roughly 10 degrees in the sky, about 20 times the diameter of the full moon. Subsequent observations by the Planck satellite confirmed the anomaly, ruling out instrumental errors or data artifacts. Statistical analyses suggest there's only about a 1 in 50 chance that such a dramatic temperature fluctuation would occur randomly within the standard cosmological model, supervoid explanation. In 2015, astronomers using the Pan-STARRS telescope in Hawaii and the Dark Energy Survey camera discovered a supervoid aligned with the cold spot position. This supervoid, a sphere of significantly reduced matter density spanning approximately 1.8 billion light-years, could potentially explain the temperature anomaly through the integrated Sachs-Wolf effect, where photons gain energy falling into gravitational wells and lose energy climbing out. However, detailed calculations suggest this supervoid isn't quite large or empty enough to fully account for the cold spot's temperature profile, leaving the door open for more exotic explanations. Multiverse implications. Some theoretical physicists propose a more radical explanation. The cold spot might represent evidence of another universe colliding with our own. According to certain multiverse theories, particularly those involving eternal inflation, our universe might be one bubble among many in a vast multiverse. If another universe bubble collided with ours in the distant past, it could have left an imprint in the CMB precisely resembling the cold spot. While highly speculative, this hypothesis has generated significant interest because it potentially offers observable evidence for the multiverse, a concept that critics have often dismissed as untestable and therefore unscientific. Formation and evolution of cosmic voids. How emptiness grows. Cosmic voids evolve through a process often described as the Russian doll mechanism. Initial small underdensities in the early universe's matter distribution become amplified over time as gravity draws matter away from underdense regions toward denser areas. These emptier regions expand faster than their surroundings due to less gravitational restraint. Smaller voids merge into larger voids as the matter between them collapses into filaments. Over billions of years, this process creates the vast empty regions we observe today. Computer simulations of cosmic evolution show that voids naturally become more spherical over time, regardless of their initial shape. Their expansion also slows as they reach a point of stability, where the outward push balances the gravitational pull of surrounding structures. Void galaxies, life in cosmic deserts. While extraordinarily empty, voids aren't completely devoid of galaxies. The few galaxies that do reside within these cosmic deserts, known as void galaxies, exhibit distinctive properties. They tend to be smaller, bluer, and more actively forming stars than their counterparts in denser environments. They show little evidence of interaction or mergers with other galaxies. They often contain more gas relative to their stellar mass. Their evolution appears primarily driven by internal processes rather than environmental interactions. These galaxies provide natural laboratories for studying galaxy formation in isolation, free from the complex interactions that occur in denser cosmic environments. Voids as cosmological probes, testing dark energy. Cosmic voids offer unique opportunities for testing cosmological models, particularly regarding dark energy. Because voids are dominated by dark energy rather than matter, their evolution is especially sensitive to dark energy's properties. By studying how voids grow and change shape over cosmic time, astronomers can test different dark energy models with remarkable precision. The Alcock-Paczynski test, which examines the apparent shapes of cosmic structures under different cosmological parameters, works particularly well with voids due to their naturally spherical tendency. Recent studies applying this test to thousands of voids identified in the galaxy surveys have provided independent confirmation of the standard cosmological model while placing tight constraints on potential alternative theories. Challenging standard cosmology. Despite their utility in confirming aspects of the standard cosmological model, voids also present several challenges to our understanding. The void phenomenon. Computer simulations consistently predict more galaxies within voids than we actually observe, suggesting potential issues with our understanding of galaxy formation or dark matter behavior. Void alignment. Some studies indicate that voids might be aligned along preferred directions in space, potentially violating the cosmological principle that assumes uniformity and isotropy at large scales. Void emptiness. The extreme underdensity of some supervoids stretches the limits of what standard cosmological models predict. These discrepancies might point toward modifications needed in our cosmological models, potentially involving new physics beyond the standard lambda CDM framework. Probing voids, observational techniques. Void-finding algorithms. Identifying voids in observational data presents significant challenges. Astronomers have developed various computational approaches. Watershed algorithms treat galaxy distribution like a topographic map, identifying voids as basins. ZOBOV zones, bordering on voidness, identifies density depressions without assuming void shapes. Void finders based on empty spheres search for maximal empty regions within galaxy distributions. Modern galaxy surveys like SDSS, Sloan Digital Sky Survey, DESI, Dark Energy Spectroscopic Instrument, and Euclid are mapping the three-dimensional positions of millions of galaxies, enabling increasingly precise void catalogs containing thousands of cosmic voids. Gravitational lensing and void detection. One of the most promising techniques for studying voids is weak gravitational lensing, the subtle distortion of background galaxy images by foreground mass distributions. Since voids represent underdensities, they create a distinctive anti-lensing signal that can be measured statistically by analyzing millions of galaxy shapes. Recent studies have successfully detected this void lensing signal, directly confirming the mass deficiency within cosmic voids and providing an independent probe of their properties that doesn't rely on visible galaxies. Future directions and unsolved questions. Next generation void science. Upcoming astronomical projects will revolutionize void research. The Vera C. Rubin Observatory's Legacy Survey of Space and Time, LSST, will map billions of galaxies, enabling identification of voids across unprecedented cosmic volumes. The Nancy Grace Roman Space Telescope will provide precise weak lensing measurements to probe void mass distributions. The Euclid mission will measure the shapes and 3D positions of galaxies across most of the observable universe, creating the most comprehensive void catalog ever compiled. These observations will transform voids from cosmic curiosities into precision cosmological tools, potentially revealing new physics beyond the standard model. Persistent mysteries. Several fundamental questions about cosmic voids remain unanswered. What physical processes determine the extreme emptiness of supervoids? Do voids eventually merge into a single connected structure as the universe ages? Could primordial voids from the early universe provide insights into inflation and quantum gravity? Do the observed void alignments indicate large-scale cosmic structures beyond our current understanding? Could void properties provide evidence for modified gravity theories? Conclusion. Cosmic voids, the vast empty regions comprising most of our universe's volume, represent not absence but opportunity. These cosmic laboratories, relatively untouched by the complex processes affecting denser regions, offer uniquely clean environments for testing fundamental physics. From probing the nature of dark energy to potentially providing evidence for parallel universes, void science stands at the frontier of cosmology. As we map the cosmos with unprecedented precision in the coming decades, these empty regions may ironically prove filled with discovery, challenging and expanding our understanding of the universe's most fundamental properties. In the apparent emptiness of cosmic voids, we may find answers to some of the greatest questions in modern physics. Episode 3. Fast Radio Bursts, FRBs. Introduction. In the vast silence of intergalactic space, brief flashes of radio energy erupt with astonishing power, then vanish in milliseconds. These mysterious signals, fast radio bursts, FRBs, represent one of astronomy's most perplexing recent discoveries. First detected in 2007, these cosmic enigmas release more energy in a few milliseconds than our sun produces in decades, yet their origins remain largely unknown. As our detection capabilities advance, these fleeting cosmic messengers are transforming from astronomical oddities into potential tools for probing the fundamental structure of the universe. From neutron star physics to potential alien technologies, FRBs challenge our understanding of high-energy astrophysics and may ultimately provide insights into the cosmos that no other phenomenon can offer. The discovery, cosmic mysteries and archival data. The Lorimer Burst, FRB 010724. The story of fast radio bursts begins not with a dramatic real-time observation, but with a doctoral student's diligent analysis of archival data. In 2007, Duncan Lorimer and his student David Narkovich were examining 2001 data from Australia's Parkes Radio Telescope when they noticed something extraordinary. A powerful radio burst lasting just 5 milliseconds that appeared to originate from the Small Magellanic Cloud, a satellite galaxy of the Milky Way. The signal, later designated FRB 010724, or the Lorimer Burst, exhibited unusual properties that immediately set it apart from known astrophysical phenomena. It was incredibly brief, lasting just milliseconds. It showed a distinctive dispersion sweep, indicating an extragalactic origin. Its extreme brightness suggested a cataclysmic event. No counterpart emissions were detected in other wavelengths. The burst's dispersion measure, the delay in arrival times of different radio frequencies due to interactions with electrons in the intergalactic medium, suggested it had traveled approximately 375,000 light-years. This placed its source far beyond our galaxy, implying an extraordinarily energetic event. Initially received with skepticism by the astronomical community, the phenomenon gained credibility when similar bursts were discovered in other telescope data. By 2013, 4 more FRBs had been identified, confirming these signals represented a genuine cosmic mystery, from perytons to confirmed phenomenon. The path to accepting FRBs as legitimate astronomical phenomena faced a significant hurdle in 2015 when researchers discovered that some similar signals, dubbed perytons, were actually produced by microwave ovens at the Parkes Observatory when their doors were opened prematurely. This terrestrial explanation temporarily cast doubt on all FRB detections. However, the controversy was definitively resolved when the Arecibo Observatory in Puerto Rico detected an FRB from an entirely different location. Then, In 2016, astronomers using the Green Bank telescope and the Very Large Array confirmed the extragalactic nature of an FRB by precisely pinpointing its origin to a small galaxy 3 billion light-years away. The era of FRB astronomy had officially begun. Characteristics of fast radio bursts, extreme energy, and brief duration. The defining characteristics of FRBs continue to challenge astrophysical models. Duration, typically lasting 0.1 to 10 milliseconds. Energy, releasing 10 circumflex, 33 to 10 circumflex, 36 joules, equivalent to the sun's output over decades. Brightness, among the brightest radio sources ever detected. Frequency range, usually detected between 400 MHz and 8 GHz. Dispersion measure, indicating travel through the intergalactic medium. Polarization, often highly polarized, suggesting powerful magnetic fields at the source. The brevity of FRBs implies incredibly compact sources, as the emission region cannot be larger than the distance light travels during the burst duration, approximately 30,000 kilometers for a 1 millisecond burst, about 2.5 times Earth's diameter. Population statistics and distribution. As detection capabilities have improved, astronomers have now cataloged over 1,000 FRBs from various directions across the sky. Their isotropic distribution, appearing from all directions rather than concentrating along the galactic plane, confirms their extragalactic nature. Current estimates suggest that approximately 10,000 detectable FRBs occur across the entire sky every day, though most go unobserved due to limited telescope coverage. Statistical analysis reveals a diverse population with varying energies, durations, and spectral characteristics. Some FRBs show complex internal structure with multiple subpulses, while others appear as clean, single pulses. The frequency-dependent properties suggest various emission mechanisms or propagation effects through intervening plasma. The repeater revolution, FRB 121102, the first repeating FRB. The discovery of FRB 121102 in 2012 transformed our understanding of these phenomena. Unlike all previously detected bursts, this FRB didn't just flash once and disappear forever. It repeated. Between 2012 and 2018, astronomers detected over 200 bursts from this single source, definitively proving that at least some FRB sources can produce multiple events. This repeatability had profound implications. It ruled out cataclysmic, destructive events, like neutron star collisions. As the sole explanation for FRBs, it allowed for targeted follow-up observations and precise localization. It enabled detailed studies of burst properties over time. In 2017, using the European VLBI network and the 305-meter Arecibo radio telescope, astronomers pinpointed FRB 121102 to a star-forming region in a dwarf galaxy 3 billion light-years away. The source appeared to be co-located with persistent radio emission, a potential clue to its nature. Periodic patterns and activity cycles. Further study of repeating FRBs revealed another layer of complexity. Some show distinct periodicity in their activity. FRB 180916, discovered by the Canadian Hydrogen Intensity Mapping Experiment, CHIME, exhibits a 16.35-day cycle, with bursts clustering within a 4-day window, followed by 12 days of silence. Similarly, FRB 121102 demonstrates a 157-day activity cycle, with approximately 90 days of active bursting, followed by 67 days of quiescence. These patterns suggest possible orbital dynamics or rotational periods influencing the emission mechanism. The recognition of these activity windows has dramatically improved detection efficiency, allowing astronomers to schedule observations during likely active periods rather than continuously monitoring. The hunt for origins. Leading theories, magnetar model, stellar storms. The leading theory for FRB origins centers on magnetars, young neutron stars with magnetic fields 1 trillion times stronger than Earth's. These stellar remnants undergo violent processes that could potentially generate FRBs, star quakes, sudden restructuring of the magnetar's crust, releasing enormous energy, magnetic reconnection, realignment of magnetic field lines, similar to solar flares, but vastly more powerful synchrotron Maser emission, Interaction between relativistic plasma and intense magnetic fields. A breakthrough came in April 2020 when astronomers detected an unusually bright radio burst from SGR 1935 plus 2154, a known magnetar within our galaxy. Though less powerful than typical extragalactic FRBs, this event, dubbed FRB 200428, provided the first direct connection between magnetars and FRB-like emissions. The magnetar model elegantly explains many FRB properties, including their brief duration, high polarization, and enormous energy. It also accommodates both repeating and non-repeating FRBs. Some magnetar events might be rare cataclysms, while others could involve recurring processes, alternative natural explanations. While magnetars represent the most widely accepted explanation, several alternative models remain viable. Neutron star mergers. The collision of two neutron stars could generate a brief, powerful radio pulse, though this would not explain repeating FRBs blitzers. Proposed theoretical objects where supermassive neutron stars collapse into black holes, converting magnetic energy to radio emission cosmic strings. Hypothetical one-dimensional topological defects in space-time that could release energy when they interact. White hole emissions. Speculative inverse of black holes that might expel matter and energy in powerful bursts. Interactions near supermassive black holes. Neutron stars orbiting close to galactic centers could generate FRB-like emissions through various mechanisms. Each theory has strengths and limitations in explaining the diverse properties observed across the FRB population. The technosignature hypothesis. The extreme energy, regular patterns, and unexplained properties of some FRBs have inevitably led to speculation about our artificial origins. Theoretical work by Harvard astronomer Avi Loeb and others has explored whether FRBs could represent technosignatures of advanced extraterrestrial civilizations. Potential artificial sources include powerful beamed energy systems for propelling light sails on interstellar vessels, communication beacons between distant civilizations, artificial pressure pulses in plasma to transmit information. While natural explanations remain far more likely, the technosignature hypothesis has spurred valuable discussion about distinguishing artificial signals from natural phenomena. The regular periodicity of some repeating FRBs initially seemed potentially significant, but the discovery of similar patterns in purely natural sources like pulsars suggests caution in interpretation. Detection revolution, new telescopes, new discoveries. CHIME, the FRB factory. The Canadian Hydrogen Intensity Mapping Experiment, CHIME, has revolutionized FRB research since it began operations in 2018. Unlike traditional steerable dishes, CHIME consists of four 100-meter-long cylindrical reflectors with no moving parts, providing an enormous field of view that covers much of the visible sky each day. This design makes CHIME exceptionally efficient at detecting transient events. During its first year of operation, it discovered hundreds of new FRBs, more than the entire previous decade of observations combined. CHIME has been particularly effective at identifying repeating sources, discovering more than 20 repeaters that enable detailed follow-up studies. CHIME's discoveries have revealed important population statistics. The existence of two potentially distinct FRB populations, repeating versus non-repeating, differences in signal morphology between repeaters and one-off events, clustering of FRBs from specific regions of the sky, global collaboration and multi-messenger astronomy. The mystery of FRBs has inspired unprecedented international collaboration among radio astronomy facilities. Networks like MASTER, Mobile Astronomical System of Telescope Robots, and IceCube work in coordination to provide multi-messenger observations, attempting to detect counterparts to FRBs and other wavelengths or particle channels. Key facilities engaged in FRB research include Australia's ASKP, Australian Square Kilometre Array Pathfinder, China's FAST, 500-meter aperture spherical telescope, South Africa's Meerkat radio telescope array, the European VLBI network Puerto Rico's former Arecibo Observatory, the Allen Telescope Array in California. These diverse instruments provide complementary capabilities, from FAST's exceptional sensitivity to ASCAP's precise localization abilities. FRBs as cosmic tools. Probing the intergalactic medium, beyond their intrinsic mystery, FRBs offer valuable tools for studying the cosmos. The dispersion of radio frequencies as FRBs travel through space provides direct measurements of the electron content along their paths. This allows astronomers to probe the elusive intergalactic medium, the tenuous plasma between galaxies that contains the majority of the universe's baryonic, ordinary matter. By analyzing the dispersion measures of hundreds of FRBs from different distances and directions, scientists are building a three-dimensional map of cosmic baryonic matter distribution. This addresses the missing baryon problem, the discrepancy between the amount of ordinary matter predicted by cosmological models and what we directly observe in galaxies and galaxy clusters. Cosmological applications. FRBs may ultimately serve as cosmological probes, offering independent measurements of fundamental parameters, the Hubble constant. By correlating FRB dispersion measures with their host galaxies' redshifts, astronomers can potentially resolve the tension between different measurements of the universe's expansion rate, dark energy properties. Large samples of FRBs could constrain the equation of state of dark energy. The epoch of reionization. The dispersion measures of very distant FRBs could reveal when the universe's neutral hydrogen was ionized by the first stars and galaxies. These applications require precisely localized FRBs with identified host galaxies, a growing but still limited dataset, frontiers and future directions. Mysterious periodicity and emission mechanisms. The complex periodicity observed in some repeating FRBs presents one of the field's most intriguing puzzles. The 16.35-day cycle of FRB 180916 and the 157-day cycle of FRB 121102 suggest orbital dynamics or precession effects that remain poorly understood. Recent observations have revealed even more complex patterns, including frequency-dependent activity windows. The burst appears at different radio frequencies during different parts of its cycle. Evolution of burst properties over time. Clustering behavior within active periods. Theoretical models continue to evolve to accommodate these observations, with recent proposals including binary magnetar systems or interactions between magnetars and surrounding debris disks. Upcoming facilities and prospects. The next decade promises exponential growth in FRB science through new facilities. The Square Kilometres Array, SKA, this international radio telescope project in Australia and South Africa will provide unprecedented sensitivity for FRB detection, potentially discovering thousands of events daily. The DSA 2000, a planned array of 2,000 dish antennas in the American Southwest, specifically designed for FRB studies, burst triggering telescope. A dedicated FRB detection system under development in Canada. These instruments will not only increase the raw number of detected FRBs, but also provide crucial capabilities for real-time follow-up observations across multiple wavelengths. The goal is to catch FRB counterparts, emissions in optical X-ray or gamma-ray wavelengths that might accompany the radio bursts and provide additional clues to their origins. Conclusion. Fast radio bursts represent a perfect cosmic mystery, powerful enough to be detected across billions of light years, yet brief enough to challenge our observational capabilities, energetic enough to demand exotic physics, yet diverse enough to suggest multiple underlying phenomena, rare enough to have eluded detection until recently, yet common enough to occur thousands of times daily across the sky. As detection capabilities advance and theoretical understanding evolves, FRBs are transitioning from enigmatic curiosities to valuable astrophysical tools. Their brief flashes carry information about their mysterious sources, the intervening intergalactic medium, and potentially the fundamental structure of the cosmos itself. Whether they ultimately prove to be primarily magnetar eruptions or reveal multiple distinct phenomena, FRBs illuminate the dynamic, energetic universe where extreme physics produces effects we're only beginning to understand. The ongoing global effort to capture, characterize, and comprehend these cosmic messengers represents one of the most exciting frontiers in modern astronomy, a quest that may ultimately transform our understanding of the most energetic processes in the universe. Episode 4: Black Hole Paradoxes. Introduction. At the intersection of extreme gravity and quantum mechanics lies one of physics' most profound battlegrounds: black holes. These cosmic titans, where matter collapses to infinite density and space-time curves so severely that not even light escapes, have evolved from mathematical curiosities to observed astrophysical objects. Yet, beyond their event horizons lurk paradoxes that threaten the foundations of modern physics. The principles that successfully describe the universe at its largest and smallest scales, general relativity and quantum mechanics, come into direct conflict in the black hole environment, producing contradictions that have bewildered the greatest scientific minds for decades. These paradoxes aren't merely abstract puzzles, but windows into deeper physics, potentially guiding us toward a unified theory of quantum gravity. In this episode, we explore how these enigmatic objects have become crucial laboratories for testing fundamental theories, forcing us to reconsider our most basic assumptions about information, causality, and the fabric of reality itself. The Information Paradox, a Crisis in Physics. Hawking's Bombshell. In 1974, a young Stephen Hawking shocked the physics community with a discovery that would define much of his career. Black holes aren't entirely black. By applying quantum field theory to the curved space-time around black holes, Hawking demonstrated that these objects should emit radiation, later named Hawking radiation, through a quantum process near the event horizon. While revolutionary in itself, this discovery led to a profound crisis in physics. According to quantum mechanics, physical information cannot be destroyed. The complete data about every particle's state must be preserved, even through transformations, a principle known as unitarity. Yet, Hawking's analysis suggested that black holes evaporate completely over time, apparently destroying all information about what fell in. This information paradox presents a stark choice. Either information is permanently lost, violating quantum mechanics, or information somehow escapes the black hole, seemingly violating general relativity's prohibition on faster-than-light travel from beyond the event horizon. Hawking initially argued that information was indeed lost, famously betting against physicists John Preskill and Kip Thorne in 1997. The stakes were modest: an encyclopedia for Preskill if information is preserved, a baseball encyclopedia for Hawking if information is lost. But the implications were enormous. After nearly 3 decades defending information loss, Hawking conceded the bet in 2004, announcing that he believed quantum effects would preserve information. However, his concession offered no definitive resolution to the paradox, which continues to drive theoretical research today. Quantum information theory perspective. Modern approaches to the information paradox increasingly draw from quantum information theory, treating information in terms of quantum bits or qubits rather than classical information. The framework of quantum error correction has proven particularly valuable. Quantum computers employ error correction codes to protect information from decoherence by distributing it across multiple entangled qubits. Similarly, holographic approaches to quantum gravity suggest information falling into black holes might be encoded redundantly across the event horizon, preserving it even as the black hole radiates. This interpretation connects to a broader concept known as quantum error correction codes, mathematical structures that protect quantum information by encoding it across multiple qubits. Recent work by physicists like Daniel Harlow and Patrick Hayden suggests the fabric of space-time itself might function as such a code, naturally preserving information through entanglement structures. The firewall paradox, a burning question. Amps and the horizon problem. In 2012, 4 physicists, Ahmed Almhairi, Donald Marolf, Joseph Polchinski, and James Sully, collectively known as AMPS, identified a dramatic inconsistency in black hole physics that became known as the firewall paradox. Their analysis revealed that 3 widely accepted principles cannot simultaneously be true. Hawking radiation is in a pure quantum state, preserving unitarity. Effective field theory is valid outside the horizon. Physics works normally in low curvature regions. An observer falling into a black hole sees nothing special at the horizon. The equivalence principle holds. According to AMPS, if information escapes the black hole via Hawking radiation, principle 1, and physics works normally near but outside the horizon, principle 2, then principle 3 must fail. They propose that anyone falling into a black hole would encounter an enormously energetic firewall at the horizon, a wall of pure energy that would incinerate them, contradicting Einstein's equivalence principle. This proposal was revolutionary because a fundamental tenet of general relativity is that nothing special should happen at the event horizon from the perspective of a falling observer. The firewall solution preserves information, but sacrifices the smoothness of space-time at the horizon, directly challenging Einstein's theory. Proposed resolutions. The firewall paradox has generated numerous proposed resolutions, each with profound implications. Complementarity. Proposed by Leonard Susskind and Gerard Hooft. Black hole complementarity suggests the experiences of an observer falling into a black hole and one remaining outside can be irreconcilably different, yet both valid, akin to the wave-particle duality in quantum mechanics. Information can both fall in for the infalling observer and escape for the outside observer. ER equals sign EPR. In 2013, Juan Maldacena and Leonard Susskind proposed an audacious solution connecting quantum entanglement with wormholes. Their ER equals sign EPR conjecture, named after Einstein-Rosen bridges and Einstein-Podolsky-Rosen entanglement, suggests that entangled particles are connected by microscopic wormholes. In this framework, information can escape a black hole through quantum teleportation via entanglement, without violating relativistic causality. Fuzzballs. String theory proposes fuzzballs as alternatives to classical black holes, objects with no true event horizon or singularity, instead consisting of a quantum fuzz of fundamental strings. Information isn't truly trapped, as there's no classical event horizon from which it cannot escape. Gravitational collapse never completes. Some proposals suggest that due to quantum time dilation effects, black holes never fully form from an outside observer's perspective. The collapsing matter asymptotically approaches horizon formation, but never quite reaches it, avoiding the paradox altogether. None of these proposals has achieved consensus, and the firewall paradox remains an active area of theoretical investigation, driving progress toward a theory of quantum gravity, black hole entropy, and the holographic principle. Bekenstein-Hawking. Entropy. In the early 1970s, Jacob Bekenstein proposed that black holes should have entropy proportional to their horizon area. Hawking's subsequent work confirmed this insight, leading to the Bekenstein-Hawking entropy formula. SK 4LP2, where S is entropy, K is Boltzmann's constant, A is the horizon surface area, and LP is the Planck length. This result was revolutionary for multiple reasons. It suggested black holes obey thermodynamic laws, like ordinary physical systems. It implied black holes have microstates, like any thermal system. Most surprisingly, it revealed that a black hole's entropy scales with its surface area, not its volume. This area scaling behavior contrasts sharply with ordinary physical systems, whose entropy scales with volume. For a black hole the size of our solar system, the entropy would be approximately 10 circumflex, 54 times greater than the entropy of the Sun itself, an astonishing difference. The area-entropy relationship hints at a deeper truth about information storage in gravitational systems, suggesting that the maximum information content of any region of space might be proportional to its boundary surface area rather than its volume. The holographic universe. The connection between entropy and area led Gerard Hooft and Leonard Susskind to propose the holographic principle in the 1990s. This principle states that all information contained within a region of space can be represented as information on the boundary of that region, similar to how a two-dimensional hologram can encode a three-dimensional image. This counterintuitive idea suggests our three-dimensional reality might be encoded on a two-dimensional surface, with gravity emerging from this encoding. The principle gets its strongest support from the ADS-CFT correspondence discovered by Juan Maldacena in 1997, which provides a precise mathematical relationship between a gravitational theory in anti-de Sitter space and a quantum field theory without gravity on its boundary. The holographic principle resolves the black hole information paradox by showing how information about everything that falls into a black hole could be stored on its event horizon rather than lost at the singularity. When the black hole radiates, this surface information gradually transfers to the radiation. Recent work by Netta Engelhard and others has further clarified how information encoded on black hole horizons evolves during evaporation, potentially preserving unitarity while avoiding firewalls. Quantum black holes and loop quantum gravity. Beyond the singularity, classical general relativity predicts that matter collapsing into a black hole forms a singularity, a point of infinite density where space-time itself breaks down. However, most physicists believe quantum effects should prevent true singularities from forming. Loop quantum gravity, LQG, a leading approach to quantum gravity developed by Carlo Rovelli, Abhay Ashtekar, and others, suggests space-time itself has a discrete quantum structure at the smallest scales. In the LQG framework, the black hole singularity gets replaced by a quantum bounce. Matter collapses to extreme but finite density before rebounding into a new region of space-time, possibly forming a white hole that ejects matter. This bounce scenario potentially resolves information-related paradoxes by allowing information to continue through the bounce, avoiding permanent trapping at a singularity. It also suggests our universe might have originated from such a bounce in a previous cosmic cycle. Planck stars and black hole remnants. Related to bounce scenarios is the concept of Planck stars, proposed by Carlo Rovelli and Francesca Vidotto. These theorized quantum objects would form when collapsing matter reaches Planck density, approximately 10 circumflex 93 grams per cubic centimeter. At this extreme density, quantum gravitational pressure would counteract further collapse. A Planck star would initially appear like an ordinary black hole, but would eventually explode through Hawking evaporation after extremely long timescales. This explosion, potentially observable as gamma-ray bursts, would release the information trapped inside, resolving the information paradox. An alternative proposal suggests black holes might never completely evaporate, instead reaching a stable minimum size as black hole remnants. These remnants could store all the information about collapsed matter, preserving unitarity while avoiding the firewall problem. However, critics note that storing the information from a stellar mass black hole would require remnants with an implausibly large number of internal states. Experimental frontiers, gravitational wave observations. The detection of gravitational waves by LIGO-Virgo collaboration since 2015 has opened a new observational window into black hole physics. While not directly testing quantum effects, these observations confirm predicted merger behaviors and provide precise measurements of black hole properties. Future gravitational wave observatories like the space-based LISA, Laser Interferometer Space Antenna, will detect smaller perturbations in space-time, potentially revealing subtle quantum effects or deviations from classical general relativity near black hole horizons. Event Horizon Telescope and black hole imaging. The Event Horizon Telescope, EHT, collaboration made history in 2019 with the first direct image of a black hole shadow, the supermassive black hole in galaxy M87. In 2022, they followed this achievement by imaging Sagittarius A*, the black hole at our Milky Way's center. These images confirm the basic predictions of general relativity about the size and shape of black hole shadows. Future enhancements to the EHT may detect subtle quantum effects manifesting at horizon scales, providing observational constraints on theoretical proposals. Analog black hole systems. While quantum effects around astrophysical black holes remain challenging to observe directly, researchers have developed laboratory systems that mimic black hole physics. These analog black holes include acoustic black holes, fluid systems where sound waves cannot escape from regions of supersonic flow, optical black holes, nonlinear optical media where light becomes trapped, Bose-Einstein condensates, quantum systems exhibiting horizon-like boundaries, Experiments with these systems have already observed analog Hawking radiation, providing indirect support for Hawking's theoretical predictions. While not testing all aspects of black hole quantum mechanics, these analog systems provide valuable insights into quantum field behavior in curved spacetime. Philosophical implications. The nature of information. The black hole information paradox forces us to reconsider what we mean by information at the most fundamental level. Quantum information theory suggests information might be neither created nor destroyed, yet its accessibility and locality can vary dramatically. Some philosophers of physics argue the paradox reveals that information must be viewed as a relational rather than absolute property. Information exists only in the correlation between systems, not as an intrinsic property of any system alone. This perspective aligns with interpretations of quantum mechanics that emphasize entanglement as fundamental. Space-time emergence. Many approaches to the black hole paradoxes suggest that space-time itself might be emergent rather than fundamental, arising from deeper quantum information structures. In this view, concepts like locality, causality, and continuity are approximate macroscopic notions that break down in extreme scenarios like black hole evaporation. Physicist Nima Arkani Hamed notes that space-time concepts like distance and duration might be doomed to be replaced by more fundamental relational properties involving quantum information. This perspective represents a profound shift in our conception of reality, comparable to the relativistic revolution of the early 20th century. Conclusion. Black hole paradoxes stand at the frontier of theoretical physics, where our most successful theories, general relativity and quantum mechanics, come into direct conflict. Rather than representing mere puzzles, these paradoxes serve as crucial guides toward a deeper understanding of nature. The intense theoretical work on information preservation, firewalls, holography, and quantum black holes has already yielded remarkable insights, including the holographic principle, ER=EPR correspondence, and connections between quantum information and space-time geometry. As observational capabilities advance through gravitational wave, astronomy, black hole imaging, and quantum simulation, we may soon obtain experimental evidence constraining theoretical proposals. Perhaps within the next decade, the profound questions raised by black holes will lead us to a consistent quantum theory of gravity, completing the revolution in our understanding of space, time, and information that black holes initiated half a century ago. In exploring these deepest mysteries of black holes, we don't merely advance specialized knowledge in theoretical physics, we redefine our fundamental conception of reality itself. The darkness of these cosmic objects may ultimately illuminate the deepest nature of the universe. Episode 5: Quantum Entanglement and Spacetime Introduction. In the fabric of reality, there exists a phenomenon so counterintuitive that Albert Einstein famously called it spooky action at a distance, quantum entanglement. When two particles become entangled, their properties become inextricably linked, regardless of the distance separating them. Measure one particle, and its entangled partner instantly reflects that measurement, seemingly communicating faster than light could travel between them. This quantum connection, once considered merely a philosophical curiosity, has evolved into one of physics' most profound and experimentally verified realities. More remarkably, recent theoretical work suggests entanglement may not just be a phenomenon occurring within space-time, it might be the fundamental process from which space-time itself emerges. From the foundations of quantum mechanics to cutting-edge theories unifying gravity with quantum physics, entanglement offers a window into the deepest structure of reality, challenging our understanding of locality, causality, and the nature of space and time themselves. This episode explores how the spooky connection between quantum particles may ultimately reveal the threads from which the cosmic tapestry is woven. Einstein's spooky action and the EPR paradox, the challenge to quantum mechanics. In 1935, Albert Einstein, Boris Podolsky, and Nathan Rosen published a landmark paper that came to be known as the EPR paradox. They identified what they perceived as a fundamental flaw in quantum mechanics. The theory seemed to allow particles to influence each other instantaneously across any distance, a direct violation of special relativity's prohibition of faster-than-light communication. Their paper described a thought experiment involving two particles created together and then separated by vast distances. According to quantum mechanics, measuring a property, such as position, of one particle would instantly determine the corresponding property of its distant partner, even before any light signal could travel between them. Einstein found this deeply troubling, as it contradicted his fundamental belief in local realism, the principle that physical reality exists independently of observation and that distant objects cannot influence each other faster than the speed of light. He argued this apparent spooky action at a distance indicated quantum mechanics must be incomplete, missing some hidden variables that would restore locality and determinism to physics. For Einstein, the EPR paradox represented not just a technical issue, but a profound conceptual problem, striking at the heart of reality itself. He maintained until his death that quantum mechanics, while mathematically successful, failed to provide a complete description of physical reality. Bohr's response and quantum complementarity. Niels Bohr, the architect of the Copenhagen interpretation of quantum mechanics, responded swiftly to the EPR challenge. He argued that Einstein's conception of reality was too restrictive. In Bohr's view, quantum properties don't exist independently of measurement. They emerge through the interaction between quantum systems and measuring apparatus. Bohr introduced the principle of complementarity, suggesting that quantum systems can exhibit mutually exclusive properties, like wave and particle behavior, depending on the experimental context. He maintained that quantum mechanics was complete and that the EPR paradox arose from applying classical intuitions to the quantum realm. The debate between Einstein and Bohr represented more than a technical disagreement. It was a philosophical clash between deterministic realism and quantum indeterminacy. For decades, this remained largely a thought experiment, with no clear way to experimentally determine which perspective was correct. Bell's inequality, from philosophy to experiment, mathematical formulation of the problem. In 1964, physicist John Stuart Bell transformed the Einstein-Bohr debate from philosophical speculation to testable science. Bell derived a mathematical inequality that any theory satisfying Einstein's local realism must obey. Crucially, Bell showed that quantum mechanics predicts violations of this inequality. Bell's approach was ingenious in its simplicity. He considered measurements of particle properties, like spin, along different axes. In any local realistic theory, the correlation between measurements on separated particles must stay within certain bounds, Bell's inequality. However, quantum mechanics predicts stronger correlations that exceed these bounds, providing a clear experimental test. This mathematical formulation moved the debate from interpretive preferences to empirical science. If experiments showed Bell's inequality was violated, Einstein's local realism would be definitively ruled out, regardless of one's philosophical inclinations. Experimental confirmations. The first experimental tests of Bell's inequality came in the 1970s, with pioneering work by physicists Stuart Friedman, John Clauser, and Alain Aspect. These experiments measured correlations between entangled photon pairs and found results consistent with quantum mechanics and in violation of Bell's inequality. However, these early experiments contained potential loopholes that could conceivably allow local realistic explanations. The locality loophole, ensuring truly independent measurements separated by space-like intervals. The detection loophole, accounting for photons that went undetected. The freedom of choice loophole, ensuring measurement settings were chosen truly randomly over decades. Progressively more sophisticated experiments closed these loopholes one by one. The culmination came in 2015 with 3 independent loophole-free experiments led by teams in the Netherlands, Austria, and the United States. All 3 definitively violated Bell's inequality while closing all major loopholes. The conclusion was inescapable. Einstein's conception of local realism had been experimentally refuted. The universe simply doesn't behave according to our classical intuitions about locality and reality. Quantum entanglement is a fundamental feature of nature, not a flaw in theory. The physics of entanglement, creating and measuring entangled systems. Quantum entanglement occurs when particles interact in ways that cause their quantum states to become interdependent. Common methods for generating entangled particles include spontaneous parametric down conversion. A laser beam passes through a nonlinear crystal, occasionally producing pairs of entangled photons. Atomic cascades. Excited atoms emit pairs of photons with correlated polarization states, quantum dots, semiconductor nanostructures that can emit entangled photon pairs, and superconducting circuits, engineered quantum systems that create entangled microwave photons. Once created, entanglement can be verified through correlation measurements. For example, with entangled photon polarizations, measuring one photon as horizontally polarized instantly implies its partner will show vertical polarization, regardless of distance. Modern experiments routinely create entanglement between dozens of quantum bits, qubits, in laboratory settings. The current record involves thousands of atoms in collective entangled states, with researchers working toward ever larger entangled systems. Entanglement properties and classification. Not all entangled states are equivalent. Physicists classify entanglement according to several criteria: bipartite versus multipartite, entanglement between two particles versus three or more, pure versus mixed. Whether the entangled system is in a single quantum state or a statistical mixture, maximal versus partial. The degree of correlation between measurements. Bell states, 4 specific maximally entangled states of 2 qubits, named after John Bell. The mathematics of entanglement uses formalisms like density matrices, Schmidt decomposition, and entanglement entropy to quantify these properties. Entanglement entropy, in particular, has emerged as a crucial concept connecting quantum information theory with fundamental physics. ER=EPR, the wormhole connection, Maldacena and Susskind's conjecture. In 2013, theoretical physicists Juan Maldacena and Leonard Susskind proposed one of the most revolutionary ideas in modern physics. Entangled particles might be connected by microscopic wormholes. Their conjecture, known as ER=EPR, suggests a profound equivalence between quantum entanglement, EPR, and Einstein-Rosen bridges, ER, the wormholes predicted by general relativity. This conjecture emerged from studies of black hole thermodynamics and the holographic principle. Maldacena and Susskind realized that the quantum mechanical description of entangled black holes remarkably resembled two black holes connected by a wormhole in the gravitational description. The implications are staggering. What we perceive as spooky action at a distance might actually involve geometry, particles communicating through shortcuts in space-time itself. Rather than entanglement violating locality, it might be redefining what local means at the quantum level. Theoretical evidence and implications. While direct experimental verification remains beyond current capabilities, theoretical evidence for ER=EPR has accumulated from multiple directions. Anti-de Sitter conformal field theory and CFT calculations show that entanglement entropy in quantum field theories corresponds to geometric quantities in their gravitational duals. Quantum teleportation protocols have gravitational analogs involving negative energy traversing wormholes. Tensor network models of entangled quantum systems naturally encode geometric structures resembling curved spacetime. If correct, ER=EPR suggests a fundamental unity between quantum mechanics and general relativity, the two theoretical frameworks that have resisted unification for a century. In this picture, entanglement isn't just a feature within spacetime, it's the thread from which spacetime itself is woven. Quantum teleportation, information transfer via entanglement, the protocol and its limitations. In 1993, a team including Charles Bennett, Gilles Brassard, and others discovered that entanglement could enable quantum teleportation, the transfer of an unknown quantum state from one location to another without physically moving the particle itself. The protocol works through a precise sequence. An entangled pair of particles is created and separated. One entangled particle interacts with the particle to be teleported. A measurement is performed, yielding classical information. This classical information is transmitted at or below light speed. The recipient uses this information to transform their entangled particle, recreating the original quantum state. Crucially, quantum teleportation does not allow faster-than-light communication. The final step requires classical information, which cannot travel faster than light. What teleports is the quantum state itself, not the physical particle. This protocol has profound implications for quantum information theory and has been experimentally demonstrated with photons, atoms, and even small groups of atoms. Record distances for quantum teleportation now exceed 1,400 kilometers, achieved by China's Messias satellite in 2017. Quantum communication networks. Quantum teleportation forms the foundation for quantum communication. Networks potentially unhackable systems for transmitting information. These networks leverage entanglement to detect any eavesdropping attempt, as measuring an entangled particle inevitably disturbs its state. China has pioneered quantum communication infrastructure, establishing a 2,000-kilometer quantum network between Beijing and Shanghai. Similar initiatives are underway in Europe, North America, and Japan, laying groundwork for a future quantum internet. Beyond practical applications, these networks serve as large-scale tests of quantum mechanics itself, verifying entanglement's properties across unprecedented distances and in novel environments. Entanglement and space-time emergence, tensor networks, and holography. A revolutionary perspective has emerged in theoretical physics. Space-time itself might emerge from quantum entanglement patterns. This view comes primarily from tensor networks, mathematical structures representing entangled quantum systems that naturally encode geometric relationships. When physicists map complex quantum systems using tensor networks, the resulting mathematics bears striking resemblance to descriptions of curved spacetime. In particular, the MERA, multiscale entanglement renormalization ansatz, tensor network, developed by physicist Glenn Evenbly and others, naturally produces a geometry with features similar to anti-de Sitter space, a curved spacetime featured in holographic theories. According to this perspective, the three-dimensional space we experience might be an emergent property arising from entanglement relationships in a more fundamental, non-spatial quantum system. Space isn't fundamental. It's what quantum entanglement looks like when viewed from our macroscopic perspective. Entanglement, entropy, and area laws. A key insight connecting entanglement to geometry comes from area laws for entanglement entropy. When calculating how much entanglement exists between a region and its surroundings in quantum field theories, physicists discovered the entanglement entropy scales with the boundary area, not the volume. This area scaling behavior mirrors the Bekenstein-Hawking entropy of black holes, which also scales with surface area rather than volume. This remarkable parallel suggests a deep connection between entanglement, information, and space-time geometry. Theoretical physicist Mark van Ramsdonk proposed that entanglement literally binds space-time together. If you could cut the entanglement between regions, space-time itself would tear apart. This perspective has gained substantial theoretical support through exact calculations in holographic models, experimental frontiers and future directions, quantum gravity experiments, testing quantum gravity. Theories directly remains enormously challenging due to the incredibly small scales involved, the Planck length, approximately 10 circumflex 35 meters. However, indirect tests involving entanglement may be more accessible. Tabletop experiments. Researchers are developing precision quantum measurements that might detect minute gravitational effects between quantum systems, satellite tests. Proposals exist for distributing entanglement between Earth and space with sufficient precision to test whether gravity affects quantum correlations, entanglement in curved spacetime. Experiments placing entangled particles in different gravitational potentials could reveal how spacetime curvature interacts with quantum correlations. While none of these experiments can currently provide definitive tests of theories like ER=sign EPR, they represent first steps toward experimental quantum gravity, a field long considered purely theoretical. Quantum simulation of spacetime. An alternative approach involves quantum simulation, using controllable quantum systems to model aspects of quantum gravity. Researchers at institutions like Harvard, MIT, and Caltech are developing quantum computers specifically designed to simulate toy models of holographic spacetime. These holographic quantum simulators aim to directly implement the math of ER=sin EPR and related conjectures, potentially providing insights into quantum gravity even before a complete theory exists. Early experiments have successfully simulated simple instances of holographic duality and teleportation through traversable wormholes in toy models. While far from modeling realistic spacetime, these simulations represent a promising bridge between abstract theoretical physics and tangible experimental results. Philosophical implications: the nature of reality and locality. Quantum entanglement forces a profound reconsideration of fundamental concepts like reality and locality. The violation of Bell's inequality conclusively demonstrates that at least one of the following must be abandoned: locality, the principle that objects are only directly influenced by their immediate surroundings; realism, the notion that physical properties exist independently of observation; counterfactual definiteness, the idea that we can meaningfully discuss the outcomes of measurements not performed. Most interpretations of quantum mechanics sacrifice at least one of these principles. For instance, the Copenhagen interpretation abandons realism, while Bohmian mechanics preserves realism by introducing non-local pilot waves. If entanglement indeed relates to spacetime geometry as ER=sin EPR suggests, locality might be preserved in a deeper sense. Quantum correlations would reflect connections through higher dimensional space, rather than truly spooky action, information, consciousness, and reality. Some researchers have proposed even more radical perspectives connecting quantum entanglement to consciousness and information. Physicist John Wheeler's famous phrase, "it from bit," suggests reality emerges from information rather than the reverse. While speculative, these perspectives highlight how entanglement challenges our most fundamental assumptions about reality's nature. If microscopic wormholes connect entangled particles, and if spacetime emerges from entanglement patterns, then information relationships may be more fundamental than physical objects themselves. Conclusion: quantum entanglement has transformed from Einstein's spooky action to a central pillar of modern physics. Its experimental verification represents one of science's greatest triumphs, definitively showing that nature doesn't conform to our classical intuitions about locality and reality. Beyond its foundational importance, entanglement has opened unexpected connections between quantum information and spacetime geometry. The ER=sin EPR conjecture and related ideas suggest entanglement isn't merely a phenomenon within spacetime. It may be the thread from which spacetime itself is woven. As quantum technologies advance, from quantum computers to satellite-based entanglement distribution, we gain unprecedented abilities to test and utilize this remarkable phenomenon. While a complete theory of quantum gravity remains elusive, entanglement provides a promising path forward, potentially unifying physics's disparate branches through the counterintuitive connection Einstein once found so troubling. Perhaps most profound are the philosophical implications. Entanglement forces us to reconsider what we mean by reality, locality, and even existence. In revealing nature's true character, it challenges us to expand our conception of what's possible and redefine our place in a universe where separation may be more illusion than reality. In the entangled cosmos, everything may be connected in ways we're only beginning to understand. Episode 6: Cosmic Microwave Background, Anomalies. Introduction: across the vastness of space comes an ethereal glow, a faint whisper of radiation permeating the universe in all directions. This is the cosmic microwave background, CMB, the oldest light in the universe, released when the cosmos was a mere 380,000 years old. Discovered accidentally in 1964, this relic radiation has become our most pristine window into the early universe, providing overwhelming support for the Big Bang theory and allowing cosmologists to determine the universe's composition and geometry with unprecedented precision. Yet, within this ancient light lies a series of perplexing anomalies, patterns and features that defy explanation within the standard cosmological model. From a mysterious cold spot spanning billions of light years to an uncanny alignment of temperature patterns, these cosmic puzzles hint at exotic physics, potential flaws in our cosmic model, or perhaps even evidence of other universes. This episode explores how the most perfect natural black body ever measured contains imperfections that may revolutionize our understanding of cosmic origins and structure, challenging fundamental assumptions about the universe's beginning and evolution. The oldest light. Understanding the CMB, the cosmic time capsule. The cosmic microwave background. Radiation represents the afterglow of the Big Bang light, released when the universe cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing photons to travel freely through space for the first time. This moment, known as recombination, occurred approximately 380,000 years after the Big Bang, when the universe had cooled to about 3,000 Kelvin. These primordial photons have been traveling through the expanding universe ever since, their wavelength stretched by cosmic expansion from visible light to microwave radiation. Today, the CMB appears as a nearly perfect blackbody spectrum, with a temperature of 2.725 Kelvin, just a few degrees above absolute zero. The CMB offers an unparalleled snapshot of the early universe. Unlike stars and galaxies that formed later, the CMB shows us the cosmos in its infancy, before complex structures developed. It's akin to a cosmic baby picture, preserving conditions from an era unreachable by any other observational method. From discovery to precision cosmology, the story of the CMB begins with an accidental discovery that ranks among the most significant in scientific history. In 1964, Arno Penzias and Robert Wilson at Bell Laboratories were testing a sensitive microwave antenna when they detected persistent background noise coming from all directions in the sky. After ruling out equipment issues, city interference, and even pigeon droppings in their antenna, they realized they had stumbled upon something profound: the remnant radiation predicted by Big Bang theorists years earlier. This discovery, which earned Penzias and Wilson the 1978 Nobel Prize in Physics, provided the first direct evidence that our universe began in an extremely hot, dense state, and has been expanding and cooling ever since. Early measurements confirmed the CMB's blackbody spectrum, but could detect only its average temperature. The true revolution began in 1992 when NASA's Cosmic Background Explorer, COBE, satellite measured tiny temperature fluctuations, variations of just 1 part in 100,000, across the sky. These minute differences represent primordial density variations that ultimately gave rise to today's cosmic structures. Subsequent missions, particularly the Wilkinson Microwave Anisotropy Probe, WMAP 2001 to 2010, and the European Space Agency's Planck satellite 2009 to 2013, mapped these fluctuations with increasing precision. By analyzing the statistical properties of these temperature variations, cosmologists determined fundamental parameters with remarkable accuracy: the universe's age, 13.8 billion years, geometry, flat, and composition, 68% dark energy, 27% dark matter, 5% ordinary matter. These results solidified the lambda CDM model as cosmology's standard paradigm, creating what many called a precision cosmology era, where theoretical predictions matched observations with unprecedented accuracy. Yet, within this triumph lurked subtle anomalies that would challenge this very paradigm. The axis of evil, cosmic alignment, problem unexpected patterns and random noise. In 2003, analyzing first-year WMAP data, cosmologists made a disturbing discovery. The largest scale temperature patterns in the CMB appeared to align along a specific axis across the sky, with cold and hot spots arranged in a way that created a distinct orientation in space. This alignment was quickly nicknamed the Axis of Evil, a somewhat tongue-in-cheek reference to President George W. Bush's recent foreign policy speech about an axis of evil among nations. This alignment manifested in the lowest multi-pole moments of the CMB, the mathematical components describing temperature variations across the largest angular scales, specifically the quadrupole, L equals sine 2, and octopole, L equals sine 3, components showed alignment not only with each other, but also roughly with the plane of the solar system and the direction of our motion through the universe. According to the standard cosmological model, CMB fluctuations should be random Gaussian noise, essentially cosmic static with no preferred direction or alignment. Finding clear directionality in these fluctuations was akin to discovering a face in television. Statics, something that simply shouldn't be there by chance. Statistical significance and controversy. The discovery immediately sparked controversy. Some researchers calculated the probability of such an alignment occurring randomly at less than 0.1%, seemingly strong evidence for a genuine anomaly. Others countered that when searching through complex data, researchers will inevitably find patterns. The question is whether those patterns are meaningful or mere statistical flukes. Further analysis complicated the picture. As WMAP collected more years of data and the Planck satellite provided independent measurements, the alignment persisted, ruling out instrumental effects or temporary phenomena. However, the statistical significance remained debated, with estimates ranging from highly significant, 1 in 1,000 chance of random occurrence, to more modest, 1 in 100. The controversy highlights a fundamental challenge in cosmology. With only one observable universe, distinguishing genuine anomalies from statistical flukes becomes exceptionally difficult. Unlike laboratory sciences where experiments can be repeated, cosmologists must draw conclusions from the single dataset nature provides, potential explanations. If the axis of evil represents a genuine cosmic feature rather than a statistical fluke, explanations fall into several categories. Local phenomena. The alignment might reflect nearby structures or our motion through space, contaminating measurements of the distant CMB exotic physics during inflation. Modified models of cosmic inflation could produce directional effects in primordial fluctuations. Topological features. The universe might have a non-trivial topology at the largest scales, creating repeating patterns, pre-Big Bang imprints. Structures from a previous cosmic cycle might have influenced the early moments of our universe and anesotropic expansion. The universe might have expanded differently along different axes during its earliest moments. Perhaps most intriguing is the possibility that the alignment reflects our position relative to a vast cosmic structure, something so large it spans much of our observable universe, yet somehow influences the primordial radiation's patterns. The cold spot, a supervoid or parallel universe, an inexplicable temperature depression. Among the CMB anomalies, the cold spot stands as perhaps the most dramatic. Located in the constellation Eridanus, this region appears approximately 70 microkelvin, colder than the average CMB temperature, a seemingly modest difference that nonetheless represents a significant statistical aberration across a vast area of the sky. The cold spot spans approximately 10 degrees in angular diameter, about 20 times the size of the full moon, and shows a distinctive temperature profile with a central cold region surrounded by a slightly warmer ring. What makes this feature particularly anomalous is its deviation from the expected Gaussian random distribution of temperature fluctuations. The cold spot appears too large and too cold to easily fit within standard cosmological models. Statistical analyses suggest the probability of finding such a feature by chance in Gaussian random fluctuations is less than 1 in 1,000, making it one of the most statistically significant CMB anomalies, the supervoid hypothesis. One prominent explanation suggests the cold spot results from a vast supervoid, an enormous region of space containing significantly fewer galaxies than average. In 2015, astronomers using the Pan-STARRS telescope and the Dark Energy Survey identified a large underdensity of galaxies in the direction of the cold spot, spanning approximately 1.8 billion light-years in diameter. This supervoid could potentially explain the cold spot through the integrated Sachs-Wolf ISW effect, where CMB photons lose energy as they pass through large-scale structures due to evolving gravitational potentials. As photons travel through a large void, they would experience a net cooling effect, potentially creating the observed temperature depression. However, detailed calculations indicate this supervoid, while real, isn't quite large or empty enough to fully account for the cold spot's extreme properties. The observed void would produce some cooling, but only about 10 to 20% of the cold spot's temperature decrement, leaving most of the anomaly unexplained. Multiverse implications. A more exotic explanation proposes the cold spot might represent evidence for a parallel universe. According to some multiverse theories, particularly those involving eternal inflation, our universe might be one bubble among many in a vast multiverse. If another universe bubble collided with ours in the distant past, it could have left an imprint in the CMB, potentially resembling the cold spot. Theoretical physicist Laura Mersini-Houghton has championed this interpretation, suggesting the cold spot represents a cosmic bruise from an interuniversal collision. Her team has even proposed the possibility of a corresponding hot spot in the opposite direction, though this has not been conclusively observed. While speculative, this hypothesis has generated significant interest because it potentially offers observable evidence for the multiverse, a concept that critics have often dismissed as untestable and therefore unscientific. If true, the cold spot might represent our first glimpse of another universe beyond our own. Power spectrum, anomalies, missing large-scale fluctuations. The suppressed large-scale power. Another persistent CMB mystery involves the power spectrum, a mathematical description of how much temperature variation exists at different angular scales. According to standard cosmological models, this spectrum should follow a specific pattern, with the amount of fluctuation power varying predictably across different scales. However, measurements from both WMAP and Planck consistently show less temperature variation at the largest scales, spanning 60 degrees or more, than predicted by the lambda CDM model. In statistical terms, the quadrupole, LL equals sine 2, mode shows only about 1/7 the expected power. This deficit persists despite increasingly precise measurements, suggesting a genuine deviation from theoretical expectations rather than observational error. The probability of such a large-scale power deficit occurring by chance within the standard model is less than 1%. Cosmic variance and observation limits. Evaluating the significance of large-scale anomalies faces a fundamental limitation known as cosmic variance. We have only a few independent samples to measure, essentially a small statistical sample size. This limitation means that even with perfect instruments, uncertainty would remain about whether large-scale features represent genuine cosmic properties or statistical flukes from our limited viewpoint. It's analogous to trying to understand ocean wave patterns by observing just a small pond. The sample may not represent the full range of possible behaviors. Despite this limitation, the consistent observation of suppressed large-scale power across multiple independent experiments suggests the effect is likely real and requires explanation. Finite universe models. One intriguing explanation involves a finite universe size. If the universe has a non-trivial topology, similar to how a video game screen wraps around when a character reaches the edge, it could create a cutoff in fluctuations larger than the universe's fundamental size. Various topological models have been proposed, including a dodecahedral universe, Poincare dodecahedral space, where space connects in complex ways, creating an effective box that constrains the largest possible fluctuations. Other possibilities include a torus topology, where the universe connects to itself along multiple axes. These models make specific predictions about patterns that should appear in the CMB if space wraps around itself, matching circles of temperature patterns on opposite sides of the sky. Searches for these specific patterns have yielded inconclusive results, neither confirming nor definitively ruling out finite universe models. Hemispherical asymmetry, a lopsided universe north-south power imbalance. Perhaps the most persistent large-scale anomaly is a subtle asymmetry in fluctuation amplitude between opposite hemispheres of the sky. First reported in 2003 and confirmed by subsequent observations, this asymmetry manifests as approximately 10% more temperature variation in one half of the sky than the other. The effect creates a distinct dipolar pattern across the sky, with fluctuation power gradually increasing from one direction to the opposite. This asymmetry extends across a wide range of angular scales and appears consistent across multiple frequency bands, ruling out simple foreground contamination or instrumental effects. Statistical analyses suggest less than a 1% probability of such asymmetry arising by chance in a standard cosmological model, making it one of the most significant CMB anomalies. Modulated primordial fluctuations. A leading theoretical explanation involves modulated primordial fluctuations, the possibility that the amplitude of initial quantum fluctuations during cosmic inflation varied across space. This could occur if inflation was influenced by a long wavelength mode of a second field, sometimes called a curvaton, creating a gradient in fluctuation amplitude across the observable universe. This scenario effectively suggests our observable universe sits off-center within a larger cosmic structure, with different regions experiencing slightly different inflationary conditions. From our perspective, this would create a gradient in CMB fluctuation properties across the sky. Some versions of this hypothesis predict specific statistical signatures beyond simple power asymmetry, including particular patterns and higher-order correlations that researchers continue to search for in CMB data. Challenges to cosmic inflation. These hemispherical anomalies pose particular challenges for cosmic inflation. The theory that the universe underwent an exponential expansion in its first tiny fraction of a second. Standard inflationary models predict statistically homogeneous fluctuations across the observable universe, making large-scale asymmetries difficult to accommodate. While modified inflationary scenarios can produce some asymmetry, creating effects as large as observed typically requires significant fine-tuning or introducing additional complex mechanisms. These challenges have led some theorists to explore alternatives to standard inflation, including bouncing cosmologies or modified gravity theories that might more naturally produce directional effects. Parity. Anomalies, mirror universe, problems, even odd multipole patterns. Another subtle but persistent anomaly involves differences between even and odd multipole patterns in the CMB. Multipoles with even values of L, quadrupole, hexadecapole, etc., show different statistical properties than those with odd values, dipole, octopole, etc. This even-odd asymmetry represents a form of parity violation, a preference for one direction of rotation over its mirror image. According to standard cosmological models, the universe should exhibit parity symmetry at large scales, with no preference between mirror image patterns. The anomaly appears particularly pronounced at large angular scales and persists in both WMAP and Planck data, with a statistical significance of approximately 99%. Primordial magnetic fields. One potential explanation involves primordial magnetic fields generated in the early universe. Such fields would have a direction and could induce parity-violating effects in the plasma that emitted the CMB radiation. For magnetic fields to explain the observed anomalies, they would need to be coherent across enormous cosmic scales and have sufficient strength to influence primordial plasma dynamics. While challenging to generate in standard cosmological models, such fields remain a theoretical possibility and could arise from exotic early universe physics or fundamental modifications to electromagnetism at high energies, chiral gravitational waves. A more exotic explanation involves chiral gravitational waves, primordial ripples in spacetime with a preferred handedness. Standard gravitational waves come in both left and right-handed varieties with equal probability, but some modified theories of gravity or inflation could produce an imbalance between the two forms. Such chiral gravitational waves would imprint distinct patterns in CMB polarization and could potentially explain the observed parity anomalies. Future precision measurements of CMB polarization may help determine whether this explanation holds merit. Observational challenges and future prospects, galactic foreground subtraction. A persistent challenge in CMB analysis involves separating the pristine cosmic signal from contaminating foreground emissions produced within our galaxy. The Milky Way emits microwave radiation through several mechanisms, including synchrotron radiation, thermal dust emission, and free emission, all of which must be precisely modeled and subtracted from observations. This foreground removal process becomes particularly challenging at the largest angular scales, where many anomalies appear. Different methods for foreground subtraction can yield slightly different results, potentially introducing systematic errors that mimic or obscure genuine cosmic features. Both WMAP and Planck teams employed sophisticated techniques to address these challenges, and the persistence of anomalies across different analysis methods and frequency bands suggests they cannot be entirely attributed to foreground contamination. Nevertheless, improved foreground modeling remains crucial for confident interpretation of large-scale CMB features. Next-generation CMB experiments. While Planck represented the pinnacle of full-sky CMB temperature measurements, achieving nearly cosmic variance-limited precision, future experiments will focus on CMB polarization, the subtle alignment of the electromagnetic field in CMB radiation. Upcoming ground-based observatories like the Simons Observatory and CMB-S4, CMB Stage 4, along with proposed satellite missions like Lightbird and PICO, will measure CMB polarization with unprecedented precision. These measurements could provide independent tests of existing anomalies and potentially reveal new features in visible and temperature data alone. Particularly relevant is the search for primordial B-mode polarization, a specific polarization pattern that would provide smoking gun evidence for gravitational waves from cosmic inflation. The amplitude and pattern of these B-modes could help distinguish between different theoretical explanations for CMB anomalies, particularly those involving modified inflationary scenarios or primordial gravitational waves. Theoretical implications. Beyond the standard model, modified inflation scenarios. The collection of CMB anomalies has inspired numerous modifications to the standard inflationary paradigm. Multi-field inflation. Models where multiple fields drive inflation can naturally produce directional effects and statistical anomalies. Non-Gaussian inflation. Scenarios that generate non-Gaussian fluctuations could explain the observed deviations from random Gaussian patterns. Anisotropic inflation. Models where space expands at different rates along different directions would naturally produce alignment effects. Open inflation. Inflation occurring within a bubble universe could explain the power suppression and some alignment effects. These modifications maintain inflation's core framework while adjusting specific mechanisms to accommodate observed anomalies. However, critics note that such modifications often require significant fine-tuning, potentially undermining the theoretical elegance that made inflation appealing initially. Bouncing cosmologies. An alternative to inflation involves bouncing cosmological models, where our universe emerged from a previous contracting phase, rather than a singular Big Bang. Such models, including loop quantum cosmology and ekpyrotic scenarios, could naturally produce some observed anomalies. In bouncing models, large-scale features might represent imprints from the previous cosmic cycle, potentially explaining directional anomalies as relics of the universe's pre-bounce state. These models make specific predictions for CMB polarization patterns and gravitational wave backgrounds that future observations could test, or multiverse signatures. Perhaps most speculatively, some theorists propose CMB anomalies might represent evidence for a multiverse, a vast cosmos containing many distinct universes, each with potentially different physical laws. In certain multiverse scenarios, our observable universe could interact with other bubble universes, creating detectable imprints in the CMB. The cold spot, in particular, has been interpreted as a potential bruise from such an interuniversal collision. While multiverse theories remain controversial, CMB anomalies offer rare opportunities for potential empirical tests of what critics have often dismissed as untestable metaphysics. Conclusion. The cosmic microwave background stands as one of science's greatest observational triumphs, providing compelling evidence for the Big Bang theory and enabling precision measurements of cosmic parameters. Yet, within this triumph lie persistent anomalies that challenge our understanding of cosmic origins and structure. From the axis of evil to the cold spot, from hemispheric asymmetry to suppressed large-scale power, these cosmic puzzles hint at physics beyond our standard cosmological model. While some anomalies may ultimately prove to be statistical flukes or observational artifacts, their collective persistence across multiple independent experiments suggests at least some reflect genuine cosmic features. The implications range from modest modifications to inflation to radical reconceptions of cosmic structure, including finite universe models, anisotropic expansion, and even multiverse scenarios. As next-generation CMB polarization experiments come online, we may obtain crucial new evidence to distinguish between these possibilities. In the patterns of ancient light from the cosmic dawn, we may yet find clues to the universe's deepest mysteries, perhaps even evidence for realms beyond our observable cosmos. The CMB anomalies remind us that even in our age of precision cosmology, the universe retains its capacity to surprise, challenge, and inspire us toward new horizons of understanding. Episode 7: Fermi Paradox and the Great Silence. Introduction. In the vast expanse of our universe, with its hundreds of billions of galaxies, each containing hundreds of billions of stars, a profound question emerges. Where is everybody? This deceptively simple query, attributed to physicist Enrico Fermi during a 1950 lunchtime conversation, encapsulates one of science's most perplexing mysteries: the apparent contradiction between the overwhelming probability of extraterrestrial civilizations and the conspicuous absence of evidence for their existence. As our understanding of planetary systems expands and our search capabilities grow more sophisticated, this great silence becomes increasingly puzzling. From optimistic interpretations suggesting we're merely listening at the wrong frequencies to sobering possibilities about the fragility of technological civilization, the Fermi paradox touches on astronomy, biology, sociology, and existential philosophy. This episode explores the enigma of cosmic silence, examining the mathematical probabilities, search efforts, and proposed resolutions to this question that ultimately forces us to consider humanity's place and future in the cosmic story. The mathematics of alien civilizations, the Drake equation, quantifying the probability. In 1961, radio astronomer Frank Drake formulated an equation that would become the cornerstone of discussions about extraterrestrial intelligence. The Drake equation attempts to estimate n, the number of detectable civilizations in our galaxy, through a series of astronomical, biological, and sociological factors, NORFP and FL phi FCL, where R, rate of star formation in our galaxy, FP, fraction of stars with planetary systems, N, number of habitable planets per planetary system, FL, fraction of habitable planets where life emerges, Phi, fraction of life-bearing planets where intelligence evolves, FC, fraction of intelligent species that develop detectable technology, L, the longevity of such technological civilizations. In years, Drake's intention wasn't to provide a definitive answer, but rather to structure the conversation about extraterrestrial intelligence around quantifiable parameters. Nevertheless, the equation structure highlights why the Fermi paradox is so puzzling. Even with conservative estimates for the biological terms, the sheer number of stars and planets suggests numerous technological civilizations should exist. Modern refinements, what we now know. Since Drake's original formulation, astronomical discoveries have substantially refined our estimates of several parameters. Star formation. Our current estimates place the Milky Way's star formation rate at approximately 3 stars per year, though it was higher in the past. Planetary abundance, FP. Once speculative, we now know planets are remarkably common. NASA's Kepler mission and other surveys indicate that most stars host planetary systems, with FP approaching 100% for many stellar types. Habitable zone planets, NN. Estimates suggest 20 to 25% of Sun-like stars host approximately Earth-sized planets in their habitable zones. For red dwarf stars, which comprise about 75% of all stars, the percentage may be even higher. These astronomical discoveries have strengthened the paradox. We now know with certainty that habitable environments are abundant throughout the galaxy. Conservative estimates suggest billions of potentially life-supporting planets exist in the Milky Way alone. The remaining biological and sociological parameters remain highly uncertain, constituting the true unknowns in the equation. However, the abundance of potential habitats makes the apparent absence of detectable civilizations increasingly difficult to explain, through probabilistic arguments alone. The Fermi paradox: formulations and implications. Enrico Fermi's original insight. The paradox's genesis came during a casual lunch at Los Alamos National Laboratory in 1950. While discussing UFO reports and the possibility of extraterrestrial visitation, physicist Enrico Fermi suddenly asked, "Where is everybody?" His question cut to the heart of a problem that had not been clearly articulated before. Fermi's reasoning was elegant. Given the age of the universe, 13.8 billion years, the relative youth of our solar system, 4.5 billion years, and the immense number of stars, countless civilizations should have arisen before humanity. Even with modest interstellar travel capabilities, such civilizations could have colonized the entire galaxy within a few million years, a mere moment in cosmic time. The absence of any evidence for these civilizations, no visitations, no radio signals, no megastructures, no artifact, constituted a paradox that could not be easily dismissed. Michael Hart's formalization. In 1975, astronomer Michael Hart published an explanation for the absence of extraterrestrials on Earth, formalizing Fermi's question into a structured argument. Hart emphasized the colonization perspective. Given sufficient time, even a single expansionistic civilization should have populated the entire galaxy. Hart calculated that with ships traveling at just 10% the speed of light, the galaxy could be fully colonized in 650,000 to 1 million years, a time span that has occurred many times over in the galaxy's 3.8 billion year history. He concluded that since we see no evidence of alien visitation, technological civilizations must be exceptionally rare or non-existent. The Copernican Principle Challenge. The Fermi paradox directly challenges the Copernican principle, the philosophical position that Earth occupies no special or privileged position in the universe. If intelligent life naturally emerges under the right conditions, and those conditions exist on billions of planets, then Earth-like civilizations should be common. The paradox forces us to consider uncomfortable possibilities. Either we are genuinely special in some way, contradicting the Copernican principle, or there's something fundamentally flawed in our understanding of how life, intelligence, or civilizations develop and behave. Philosopher Nick Bostrom has argued that this observation selection effect may be significant. We can only observe universes compatible with our existence as observers. This anthropic reasoning suggests we shouldn't be surprised to find ourselves in a seemingly rare scenario if that rarity is necessary for our existence. Search efforts. Looking for signals in the silence. SETI. 6 decades of listening. The search for extraterrestrial intelligence, SETI, began in earnest in 1960 when astronomer Frank Drake conducted Project Ozma, using a radio telescope to examine 2 nearby sun-like stars for artificial signals. Though this pioneering effort detected nothing unusual, it established the template for subsequent SETI programs. Modern SETI efforts have grown increasingly sophisticated. Radio SETI. Projects like the Allen Telescope arrays scan the skies at multiple frequencies simultaneously, focusing particularly on frequencies where cosmic background noise is minimal, the water hole between 1.4 and 1.7 gigahertz. Optical SETI. Telescopes search for brief, powerful laser pulses that might serve as interstellar beacons or communication. Artifact SETI. Astronomers analyze stellar light curves for evidence of megastructures, like Dyson spheres, or unusual infrared signatures that might indicate technological activity. The largest contemporary initiative, Breakthrough Listen, represents a $100 million, 10-year commitment to survey the million closest stars across a wide range of frequencies. Using some of the world's most powerful telescopes, it collects more data in a day than previous SETI projects gathered in a year. False alarms and tantalizing signals. Despite these extensive efforts, no confirmed extraterrestrial signals have been detected. However, several intriguing signals have briefly raised hopes. The WOW signal, detected in 1977 at Ohio State University's Big Ear Radio Telescope. This unusual 72-second burst matched expectations for an artificial signal, but never repeated despite numerous follow-up observations. Tabby's star, KIC 8462852. This star exhibited unusual dimming patterns that initially defied natural explanation, prompting speculation about alien megastructures. Subsequent analysis favors complex dust cloud arrangements, though some anomalies remain unexplained. BLC-1 Signal. In 2020, the Breakthrough Listen project detected a narrow-band signal apparently coming from the direction of Proxima Centauri. After extensive analysis, researchers concluded it was likely terrestrial interference. These cases illustrate the challenge of SETI, distinguishing genuine extraterrestrial technology from natural phenomena or human interference requires extraordinary evidence that has so far remained elusive. Expanding beyond radio, new search paradigms. Recognizing the limitations of traditional SETI approaches, researchers have expanded search methodologies, technosignatures. Beyond radio signals, scientists now search for industrial pollutants in exoplanet atmospheres, artificial night-side illumination, and waste heat signatures that might indicate advanced technology. Information theory approaches. New analytical tools examine signals for complexity patterns that would distinguish intelligent communication from natural processes. Archaeological SETI. Proposals include searching for evidence of past visits to our solar system, particularly in stable orbital regions or on bodies like the Moon, where artifacts might persist for millions of years. These expanded approaches acknowledge that our expectations for how alien civilizations might communicate or be detected may be too narrowly defined by our own technological development path. The Great Filter. Are we rare, early, or doomed? Evolutionary bottlenecks. One powerful explanation for the Fermi paradox, proposed by economist Robin Hanson, introduces the concept of the Great Filter, one or more extraordinarily difficult evolutionary transitions that prevent dead matter from giving rise to expanding, space-colonizing civilizations. This filter must be powerful enough to reduce the expected number of visible civilizations from billions to the apparent zero we observe. Crucially, this filtering could occur at various stages. Behind us. The filter may lie in events already surpassed by humanity, such as the emergence of complex cells, multicellular life, or intelligence. If true, we've already navigated the most difficult evolutionary hurdles, making us genuinely rare. Before us, the filter may lie in challenges humanity has yet to face, such as self-destruction through nuclear war, pandemic, climate change, artificial intelligence, or technologies we haven't yet developed. This more ominous interpretation suggests technological civilizations typically destroy themselves before achieving interstellar capabilities. Both. Multiple significant filters may exist both behind and ahead of us, each substantially reducing the probability of space-colonizing civilizations. The Great Filter concept explains the paradox by identifying specific points in evolution or development where the probability of advancement is extraordinarily low, bottlenecks so restrictive that few if any civilizations successfully pass through all of them. The rarity of intelligence. Among potential behind-us filters, the evolution of human-level intelligence may be exceptionally improbable. While simple life might be common throughout the universe, several factors suggest that advanced cognitive capabilities might be extraordinarily rare. Contingent evolutionary path. Human intelligence didn't evolve through a direct, inevitable trajectory, but resulted from a series of contingent events and environmental pressures that may be highly unusual. Evolutionary trade-offs. Large brains require enormous energy investment and create significant risks, difficult childbirth, extended childhood vulnerability. These costs might rarely be outweighed by survival benefits. Limited ecological niches. Advanced intelligence might only provide selective advantages in specific environmental contexts that rarely persist long enough for large brains to evolve. Paleontologist Peter Ward and astronomer Donald Brownlee have argued in their rare Earth hypothesis that, while microbial life may be common, complex multicellular life requires an unusual combination of planetary conditions that few worlds maintain over the necessary time frames. Technological self-destruction among ahead-of-us filters. The most concerning involve civilizational collapse or extinction through technological nuclear annihilation. First recognized during the Cold War, The risk of nuclear war remains a filter candidate, particularly as nuclear technology proliferates. Climate change. The inability to maintain environmental stability while developing industrial technology could be a nearly universal challenge for technological species. Biological threats. Advanced biotechnology might enable the creation of pathogens with lethality and transmissibility beyond anything in nature. Artificial intelligence. Unaligned superintelligent AI might represent an existential risk that few or no civilizations successfully navigate. Unknown technologies. We may not have discovered the most dangerous technologies yet. If virtually all advanced civilizations discover and deploy some form of self-destructive technology, this would explain the silence. Oxford philosopher Toby Ord estimates humanity's risk of extinction in the next century at approximately 1 in 6, suggesting the filter ahead may be substantial even from our current vantage point. Sociological explanations. Behaviors of advanced civilizations. The zoo hypothesis. Proposed by astronomer John Ball in 1973, the zoo hypothesis suggests that extraterrestrial civilizations intentionally avoid contact with emerging species like humanity. This deliberate non-interference policy might stem from ethical considerations. Advanced civilizations might recognize that contact with less developed species inevitably alters their independent development, similar to anthropologists' concerns about disrupting isolated human cultures. Scientific value. Civilizations might preserve Earth as a wilderness reserve or sociological experiment, studying humanity's natural development without interference. Developmental thresholds. A galactic club might exist that only contacts species after they reach certain technological or ethical milestones, which humanity has not yet achieved. This hypothesis explains the paradox. While allowing for numerous advanced civilizations, we don't detect them because they actively ensure we cannot, at least until we're deemed ready for contact. Dark forest theory. Chinese science fiction author Liu Cixin popularized the dark forest theory in his novel The Three-Body Problem. This grim hypothesis suggests that silence is the optimal survival strategy in a dangerous cosmos. Security. Dilemma. Civilizations cannot know others' intentions and cannot afford to assume benevolence. Growth. Imperative. Expanding civilizations eventually compete for finite cosmic resources. Preemptive strike advantage. It's safer and easier to eliminate potential competitors before they become threatening. Under these conditions, broadcasting one's location becomes an existential risk. Successful civilizations might remain deliberately silent and hidden, explaining why we detect no signals despite numerous advanced species. Post-biological evolution. Another possibility involves the transition from biological to technological existence. Advanced civilizations might evolve beyond recognizable forms. Digital transcendence. Civilizations might upload consciousness to computational substrates, abandoning biological existence and its constraints. Inward focus. Virtual realities could provide unlimited subjective experiences without requiring cosmic expansion, turning civilization's focus inward rather than outward. Efficiency. Imperatives. Advanced computation might minimize energy use and heat signatures, making such civilizations nearly undetectable. Incomprehensible motivations. Post-biological entities might develop goals and behaviors so different from biological evolution that they no longer engage in activities we would recognize as expansionistic or communicative. This perspective suggests advanced civilizations exist, but have transformed into forms operating on scales, timescales, or dimensions that make them effectively invisible to our current detection methods. Anthropic explanations. The simulation and rare Earth simulation hypothesis. Philosopher Nick Bostrom has proposed that advanced civilizations might create numerous detailed simulations of their evolutionary history. If such simulations become commonplace, the vast majority of conscious entities would exist within simulations rather than base reality. This creates an anthropic explanation for the Fermi paradox. Resource limitations. Simulations would likely focus computational resources on the immediate environment of the simulated observers, rendering distant galaxies as simplified models without detailed alien civilizations. Experimental design. Simulations might intentionally exclude alien contact to study isolated civilizational development. Single history focus. Each simulation might model just one technological species development to maximize computational efficiency. While philosophically controversial, this hypothesis provides a coherent explanation for why we observe a universe that appears capable of generating numerous civilizations, yet contains no evidence of them. Rare Earth hypothesis. Detailed in the book by Peter Ward and Donald Brownlee, the rare Earth hypothesis argues that while simple life might be common, complex multicellular life requires an extraordinary combination of planetary, stellar, and galactic conditions. Galactic habitable zone. Regions too close to the galactic center face excessive radiation and stellar density. Regions too far out lack necessary heavy elements. Stable planetary orbit. Earth benefits from unusually low orbital eccentricity and protection from Jupiter's gravitational influence. Plate tectonics. Essential for carbon cycle regulation and maintaining climate stability over geological timescales. Large moon. Stabilizes Earth's axial tilt, preventing chaotic climate variations that would impede complex life's evolution. Magnetic field. Protects atmosphere from solar wind erosion. Preserving habitability. Optimal stellar type. The Sun is unusually stable and long-lived compared to most stars. This hypothesis suggests that while planets are common, truly Earth-like planets with all necessary conditions for complex life may be exceptionally rare, potentially resolving the paradox. Current SETI initiatives and future directions. Breakthrough Listen and traditional SETI. The Breakthrough initiatives, funded primarily by Russian-Israeli entrepreneur Yuri Milner, represent the most well-resourced SETI effort in history. Breakthrough Listen, using facilities like the Green Bank Telescope, Parkes Observatory, and Meerkat Array. This project conducts the most comprehensive search for artificial radio and optical signals ever undertaken, surveying the 1,000,000 closest stars and 100 nearest galaxies. Signal processing innovations. Advanced machine learning algorithms sift through petabytes of data to identify potential signals of interest among the cosmic noise. Open data policy. All data is made publicly available, enabling distributed analysis by researchers worldwide. Beyond Breakthrough, institutions like the SETI Institute continue traditional radio astronomy approaches, while NASA has begun incorporating techno-signature research into its astrobiology portfolio after decades of avoiding explicit CT funding. Expanding beyond traditional CT. Recognizing the limitations of conventional CT, researchers are developing novel search strategies. METI, messaging to extraterrestrial intelligence. Rather than merely listening, some organizations propose actively broadcasting messages to potential extraterrestrial recipients. This controversial approach has sparked ethical debates about the wisdom of revealing Earth's location. Interstellar probes. Initiatives like Breakthrough Starshot aim to develop lightweight spacecraft capable of reaching nearby star systems within decades rather than millennia, potentially enabling direct exploration. Serendipitous. SETI. Leveraging next-generation astronomical facilities like the Vera C. Rubin Observatory and James Webb Space Telescope for piggyback SETI observations during their primary scientific missions. In situ searches. As robotic exploration of our solar system advances, missions increasingly include objectives to search for evidence of past extraterrestrial visitation, particularly in stable regions where artifacts might persist. These diversified approaches acknowledge that traditional radio SETI makes specific assumptions about alien technology and communication methods that may be too narrow. Resolving the paradox. Next steps. Several forthcoming capabilities may substantially constrain possible explanations for the Fermi paradox. Atmospheric spectroscopy. The James Webb Space Telescope and future observatories will characterize exoplanet atmospheres, potentially detecting biosignatures, signs of life, or technosignatures, signs of technology. Expanded frequency coverage. New radio telescopes like the Square Kilometre Array will monitor billions of channels simultaneously across unprecedented frequency ranges. In situ astrobiology, missions to potentially habitable worlds in our solar system, particularly Mars, Europa, and Enceladus, will search for evidence of independent life emergence, helping constrain the probability of life's origin. Improved census. The Nancy Grace Roman Space Telescope and ground-based surveys will provide a more complete census of potentially habitable worlds, refining Drake equation parameters. While none of these advances guarantees resolution of the paradox, collectively they should substantially narrow the range of plausible explanations within the next 2 decades. Philosophical and existential implications. The cosmic perspective. The Fermi paradox inevitably shapes our perspective on humanity's place in the cosmos. If we are indeed rare, perhaps the only technological civilization in our galaxy or even our observable universe, this carries profound philosophical implications. Cosmic responsibility. As potentially unique bearers of consciousness and intelligence, humanity would carry a special responsibility for preserving and spreading life's complexity. Future stakes. Our long-term survival would take on cosmic significance, as our extinction might represent the loss of the only technological intelligence in this region of the universe. Meaning and purpose. The apparent rarity of intelligent life might inform perspectives on meaning in a universe otherwise dominated by unconscious processes. Conversely, if the silence reflects the typical fate of technological civilizations, this carries equally profound implications about the challenges humanity must navigate to avoid a similar outcome. Existential hope and risk. The paradox directly informs assessments of humanity's future prospects. Existential hope. If the great filter lies behind us, humanity may have exceptional potential for long-term flourishing and cosmic expansion. Existential risk. If the filter lies ahead, we face grave challenges that have apparently defeated countless prior civilizations, making existential risk reduction perhaps our highest priority. Drake equation. Updating. Each year humanity survives provides Bayesian evidence updating our estimates of civilization longevity, the L term in Drake's equation. The Swedish philosopher Nick Bostrom has argued that discovering evidence of extinct simple life, like microfossils on Mars, would be an ominous sign, suggesting the filter lies after life's emergence rather than before it. Conversely, finding no evidence of life elsewhere would suggest the filter lies in life's origin, potentially placing humanity in a more favorable position. The long-term future of intelligence. If humanity successfully navigates existential risks and achieves long-term survival, the Fermi paradox informs our expectations about cosmic development. Settlement timescales. Even at modest expansion speeds, 1 to 10% of light speed, a successful technological species could settle the galaxy within a few million years, a mere moment in cosmic time. Observable signatures. Advanced civilizations utilizing significant fractions of their host star's energy, Kardashev Type 2, or entire galaxies, Type 3, should create detectable technosignatures visible across cosmic distances. Potential expansion. In the very long term, a successful civilization could potentially reach and utilize resources across billions of galaxies within the observable universe. The absence of visible large-scale cosmic engineering suggests that either such development paths are exceptionally rare, face insurmountable barriers, or manifest in ways fundamentally different from our expectations. Conclusion. The Fermi paradox represents far more than an astronomical curiosity. It constitutes a profound puzzle interweaving astronomy, biology, sociology, and philosophy. The apparent contradiction between the immense number of potentially habitable worlds and the absence of detectable extraterrestrial intelligence challenges our deepest assumptions about life, technology, and cosmic development. Proposed resolutions span an extraordinary range. Perhaps complex life is vanishingly rare. Perhaps technological civilizations invariably self-destruct. Perhaps advanced intelligence evolves toward undetectable forms. Or perhaps we are indeed alone, or among the first technological species in our cosmic vicinity. Each possibility carries profound implications for humanity's place in the universe and our potential future. If we have indeed passed the Great Filter, humanity may have an exceptional cosmic destiny ahead. If the filter lies before us, identifying and navigating these challenges becomes our paramount task. As our search capabilities advance and our understanding of life's emergence deepens, we progressively constrain the range of viable explanations. Yet, the silence persists, a cosmic mystery that continues to inspire wonder, concern, and determined exploration. From Fermi's simple question, "Where is everybody?" emerges one of science's most profound enigmas, and a question that ultimately leads us to reconsider what it means to be a conscious, technological species in a vast and apparently silent cosmos. Conclusion. As we've explored throughout this series, the universe presents us with mysteries that challenge our deepest understanding of reality. From dark matter and cosmic voids to quantum entanglement and the matter-antimatter asymmetry, these puzzles remind us that our cosmic journey of discovery is far from complete. Each question we've examined represents not just a gap in our knowledge, but an opportunity to expand our understanding of the fundamental nature of existence. The coming decades promise exciting breakthroughs as new technologies, observatories, and experimental techniques bring us closer to answers. Perhaps most remarkable is that we humans' collections of atoms formed in ancient stars have developed the curiosity, intelligence, and tools to investigate these profound cosmic mysteries. Our quest to understand the universe is itself one of the universe's most fascinating phenomena. Final message. If you've enjoyed this journey through the unexplained mysteries of the universe, please take a moment to like this video and subscribe to our channel for more explorations of cosmic enigmas. Share with fellow space enthusiasts who appreciate the wonder of our mysterious universe. What cosmic mystery intrigues you most? Let us know in the comments below, and we might feature your question in an upcoming episode. Until next time, keep looking up and wondering about the extraordinary cosmos we call home.